right? We said this chimney was at 44 degrees C, and T infinity was 10 degrees C. And we did that because then the average temperature was 300 Kelvin, right? The film temperature. Let's talk about convection. I want to focus on that, right? In this case, do we have an external velocity imposed? No, we did not impose one. I want to discuss today a case in which we do impose an external velocity, right? But I want to start. So if we do not have an external velocity imposed, is this an only conduction problem? No, right? Because the air gets hot, and then as it tends to go up, this creates a velocity, right? That's the point of natural convection. It's like an engine, right? It's, the thing generates its own velocities. This is one of the reasons when you see soot that it goes up, right? Is because as the hot air wants to go up, right? And has this boundary layer that causes shear and brings the hot parts up. Okay, so in this case, we would have this type of flow of air. Now, this problem had an interesting twist, and is that what we have taught you is the correlations for a vertical plate. Now, this is not a plate as far as I know, right? This is a quite round chimney. Why was it okay to use the correlations of a flat plate if we're talking about a chimney? Right, it's always the same story with convection. Always, no exception. Convection is conduction through a boundary layer, thermal boundary layer. If that thermal boundary layer is thin, right, or the radius is large compared to it, so it's as if it was painted. And I don't care anymore if it was a flat plate, a cylinder, or something with funny shape, as long as the radius of curvature is long. That's the reason we use this regression. And actually, there was a criterion that said if the diameter is bigger than something with a Grashof number, is good, right? And you have that. We have it in the slides, and it's in your notes. And all that says is, yeah, the boundary layer should be thin. That's all the whole story, right? And so we have an external velocity imposed here, and it's kind of this funny business because on the surface, the velocity is 0, far away is 0. So somewhere in between, we have this curve. We have been assuming so far that the vertical plate, right? If you remember, we would put the vertical plate here. If it is hot, we develop this boundary layer here. This is Ts, this is T infinity, and so this would be YCT, right? And we said, in this case, T infinity is less than Ts, but we said Ts, this was constant, right? Now, sometimes it's not constant. Sometimes you have other conditions. So let's think of another relevant condition. All these are idealizations. Temperatures are never exactly constant. Let's think of another condition that would be constant heat flux, right? And this goes back again to our semi-infinite solid. If you remember, we had the constant surface temperature, constant heat flux, and we had different correlations, different formulas for those. Anybody remembers how different were what we had learned for a constant surface temperature boundary condition and the constant heat flux boundary condition? Was it very different? Similar? No. we said it's pretty much all the same. One was 1 over square root of pi, and the other was like one was square root of pi, and the other was 2 over square root of pi, right? And in the end, it's not exactly the same, but kind of not the same order of magnitude. So, first tip is, in this case, we have a constant surface temperature, and I gave you all the regressions. If you have a constant heat flux, right, what are you going to do? And what the book recommends, you know what? Let's assume the constant heat flux is a constant surface temperature. Here's the catch. What temperature now? Right? Because the constant heat flux doesn't give you a temperature, right? It's just the heat flux. So this is what we have here. And what it says for vertical plates, what you assume is use constant temperature formulas. In this case, TS, now instead of TS, we would use TS of L over 2, right? So if the plate had a length L, and this is what the book calls TL over 2. Delta T is now delta T at L over 2. I know there is something interesting that happens. I'll just go quickly over this. But when you see formulas like this thing to the 1/5, that's a not common exponent. And it's not that it's empirical, and it's not that it comes from nowhere. But I'll just do a couple lines of the calculation so you see how the things come together. It's not about you reproducing this in the exam, but it's just about getting your head working together on this, putting the concepts together. So you see that says the delta Tx is x proportional to x to the 1/5. It comes from here. So we know this. This one we know because in week 2 of class we went over this, right? The heat flux is H times delta T. Now, what you have learned this week, you know what the x means here, right? That the characteristic length is x. If I put an L, it's a length, and if I put a D, it's a diameter. So it is important to put it there so we know what we're talking about. And we have that this is proportional. Look, Rayleigh, if it is laminar, right, is proportional to Rayleigh to what power? This is proportional to Rayleigh to the 1/4 over x. And if you remember Rayleigh proportional to x cubed delta t. So we have here then an h is proportional to the x to the minus 1/4, right? 3/4 here minus 1, the minus 1/4, and the delta t to the 1/4 here. So if I put this here, we have that Q is proportional to the x to the minus 1/4, delta t to 5/4. Right? This delta t is 4/4 and 1 is 5/4. Now, we said that our boundary condition is constant heat flux, right? So this is constant. And if that is constant, delta t, right, will be proportional. I can send this there and solve the exponents. Would be to x to the 1/4 raised to the 4/5. This is x to the 1/5. So when we have a constant q double prime, right? The thickness, the difference in temperature between this is T infinity and this is surface temperature, right? This difference. I just wanted to go through this because it was putting together these issues of Rayleigh, and the book doesn't say, but when they assume x to the Rayleigh to the 1/4 for the Nusselt number, they're assuming laminar, right? They don't say, but it's not for turbulent. The point here is if the boundary condition is constant heat flux instead of constant temperature, you would use the same correlations. The same correlations, just using them for half the plate, right? And it's a very good approximation, at least according to the book. And it all comes together to what we first discussed about the semi-infinite solid.